Welcome to Chapter 5, Part 2, Enthalpy and Enthalpy of Reaction. So we've started talking about energy, and so one of the things in chemistry is that we often think a little bit more about enthalpy, which is H. And so chemical changes are present all around us. Under constant pressure, enthalpy is heat flow. So enthalpy is going to measure the heat flow that surrounds us. And so this makes a lot of sense. We've talked a lot about Q, and so we can think about that. So to calculate the enthalpy, we generally use H, which is the enthalpy, equals the energy plus pressure volume. And so in this case, enthalpy is H equals E plus PV. Now, you might remember that I said that energy can't be calculated at a specific time. So we can't really solve for E, but we can calculate the change. So we know that if we want to calculate the change in H, it's going to be equal to change in E plus the change in P times V, which is equal to delta E plus delta P times V, or delta E plus pressure times the change in volume. So the difference here is that only one can change. Only one can change. So it's either at constant volume or at constant pressure. And so we can either change the pressure. So if it's at constant volume and it gets bigger, we're going to change the pressure inside the system, or the pressure will be the same and the volume of the system will change. And so we know that in this case, the delta always means final minus initial. Whoa. INIT. And so that's going to be true no matter what we're looking at the change in. And so when we think about this, we can start to think about what it means for the change in enthalpy. But one of the things we want to be able to think about is actually, what does that actually mean? And so if we think about this equation, we know that delta E equals Q plus W. And so it turns out that delta H can also equal Q plus W plus P delta V. So this is a version of that equation. So one of the things we didn't talk about in the last chapter was that one of the ways that we can calculate work is actually in this equation here. Work equals negative P delta V. So work is pressure volume work. So this is at constant pressure we can change the volume. So in this case, what we see here is that when we have positive volume, we will get negative work, and so the work is done by the system. So basically, if it gets bigger, if we think about this as a balloon, if we have one size balloon, and at the end we have a bigger balloon, we did work on surroundings. If, in this case, if we started at this size and over time we got much smaller, this is work done on the system. So basically the balloon can get bigger and smaller, and the system or the surrounding is going to squish this in either way. As we start to think about this, I want to reflect back to, so delta H equals delta E plus P delta V. So if we rewrote that as delta H equals Q plus W plus P delta V. We also know that work negative P delta V plus P delta V. So in this case, both of these will cancel, and delta H equals Q. So the enthalpy is equal to the heat in most of these situations. And so this is going to come up a lot in this chapter. And so we're going to look at different ways on how to calculate the change in enthalpy for a system. So let's look at an example here. So if fuel is burned in a cylinder equipped with a piston, the initial volume of the cylinder is 0.250 liters, and the final volume is 0.980 liters. If the piston expands against a constant pressure of 1.35 atmospheres, how much work in joules is done? So the equation we want to use is work equals negative P delta V. So pressure, in this case, is 1.35 atmospheres. And the volume final is 0.980 liters. The initial volume is 0.250 liters. So delta V is going to equal 0.730 liters. So we can plug this into our calculation as negative 1.35 atmospheres multiplied by 0.730 liters. So when we plug this into our calculator, you should get negative 0.9855 liter atmospheres. So it turns out that the answer is asked for how much work is done in joules. So we can use something called a unit conversion for liter atmospheres. So liter atmospheres isn't what it's asking for. It's also not typically a work unit. So what we're going to do is we are going to convert that. So negative 0.9855 liter atmospheres. So in 1 liter atmosphere, it is 101.3 joules. And when you plug this into your calculator, you'll get negative 99.8 joules. So if you're wondering where that information came from, it's right here in the question. And you would find that on an equation sheet. So in these questions, we can start to think about, and we could have solved for the pressure or the volume or the change in volume. We could look at any number of these over time. So we've calculated the work, and we've thought about the fact that we can look at different parts of this, and we could calculate delta H or delta E. So now we want to start to think about calculating the enthalpy of a reaction. So I misspelled this, and so I fixed it. But the enthalpy of a reaction. So now we want to know how much energy is gained or lost during a reaction. So what does that mean? So delta H is going to tell us how much energy it costs to perform a reaction. Or how much we gain. So we do have reactions where as they happen, energy is given off or heat is given off. And so when we think about this, we want to know how much energy it takes to get from products to reactants, or how much energy is released as we go from products to reactions. So because we know delta H is a state function, we know that we could calculate that. Delta H equals final minus initial. Let's think about this in terms of the fact that this is a reaction. So if we have a reaction where A plus B goes to C, the delta H of the reaction is going to be the final minus the initial. So it will be the H of the products minus H of the reactants. And so we can start to think about that. And so the other part of this that we kind of want to think about is that when delta H is positive, the reaction is endothermic. So the system absorbs heat. When delta H is negative, the reaction is exothermic. Heat is lost to the surroundings. So I always like to give tips and tricks for how I think about this. Exo, I think of an explosion where things go out to surroundings. And endothermics, endo equals into in my mind. And so it goes into the system. And so when we think about an exothermic reaction, heat is lost to the surroundings, and so it feels hot. And so endothermic, it goes into the system, so it will actually feel cold. And so this is always a little tricky, but it's endothermic. So as the heat goes inside, what you touch on the surroundings should be cooler. So as we continue to think about delta H, delta H of reaction can be thought about how much energy does it take us to go from products to reactants. So if we think about this in terms of a reaction diagram where we have enthalpy, and if we want to go from 2H2 plus O2 to 2H2O, this is our reaction here. And so this is going to tell us how much energy it's going to take. So in this case, it's going to take negative 483.6 kilojoules. So the delta H of reaction just tells us how much energy it's going to take. So this tells us that the system gives off heat to form water in this case. And so this is our delta H reaction. So the delta H reactions come from a number of different things. So delta H reaction can be calculated. And we're going to look at 3 different ways in this chapter and 1 in a later chapter. So we can calculate that using calorimetry. We can use Hess's law. And we can use heats of formation. Or we will learn in chapter 8, we can use bond enthalpy. And so we can calculate it. You can also find it, we'll say read in a table. There are large books where you can go in and calculate delta H of reaction by basically looking stuff up in these tables. But what we're going to do over the next several videos is learn how do we calculate delta H of reaction. So when we think about doing that, there are a couple of things we need to remember. So we have some guidelines. So enthalpy is an extensive property. So delta H is proportional to the amount of reactant consumed or product created. It doesn't matter how you think that. So for step 1, this basically means if delta H reaction for the combustion of methanol, which the equation for that is CH4 plus 2O2 goes to CO2 plus 2H2O. If in this case it's equal to negative 890 kilojoules, if you start with 2CH4 plus 4O2, delta H reaction is also going to be multiplied by 2. And so in that case, it would be negative 1780 kilojoules. So what it is in point 1, what it's trying to say is that basically the more reactant you have or the less product you have, either way, it is going to be proportional. So number 2, the second guideline is the enthalpy change for a reaction is equal in magnitude but opposite in sign for the reverse reaction. So if we still think about this combustion of methanol, we know that the delta H of that reaction is negative 890 kilojoules. So if we take CO2 plus 2H2O and instead get CH4 plus 2O2, instead of it giving off energy, we're now going to have to put in the same amount of energy that we would have gained. So the delta H of reaction is going to be positive 890 kilojoules. So it tells us that it's the same amount of energy if we want to go this direction, if delta H equals 5, to go in the reverse direction, delta H is just going to equal negative 5. So it is the exact same size, just different. And so the last thing, and probably the more important thing, is that the enthalpy of a reaction depends upon the states of the reactants and products. So in the equation I gave you, it doesn't have any states, but in most of the other things, it's going to matter whether we're thinking about H2O liquid, H2O gas. We don't tend to think about H2O, but it does come as a solid. So the states tell us about the energy. So it requires a change in energy to go from solid to liquid and liquid to gas. Basically, we have to add heat. So all of this is possible. So let's think about what this means in terms of this reaction. So how much heat is released with 4.50 grams of methane burned in a constant pressure system? So we have delta H reaction here, and it equals negative 890 kilojoules. Now, there is no denominator on this value, but it turns out that delta H equals negative 890 kilojoules per 1 mole of CH4. It equals negative 890 kilojoules per 2 moles of O2. It equals negative 890 kilojoules for every 1 mole of CO2. And it equals negative 890 kilojoules for 2 moles of H2O. So the important fact here is that this delta H value is your negative 890 kilojoules per any amount in problem, in the equation, we'll say that. So when this starts to come into play is when we want to ask about the heat released per maybe only 5 grams of O2. So let's think about our 4.5 grams of methane. So we want to take our 4.50 grams of CH4, and we're going to convert that using the stoichiometric ratio of 16.05 grams in 1 mole of methane. And that's going to equal 0.280 moles of CH4. So we're going to take our negative 890 kilojoules, and based on the equation here, you can see that it's only 1 mole of methane. We're going to multiply that by the number of moles that we used, which is 0.280 moles of CH4. And so in this case, we're going to get that it's negative 250 decimal point kilojoules. And so in this case, the values here are going to be dependent both on the state of our reactant and product and the stoichiometric coefficients that we're going to see.